So I'm really pleased to have you all welcome to the last colloquium of the semester. And I think a lot of you are probably getting ready for exams next week. And I know that it's a very busy time of the semester, and we have such a good turnout in spite of all of that going on. So I really appreciate that. I just put in a plug for the colloquium series as one of the important weekly events for NCSA. So everybody should be trying to make this a part of their weekly event, because we spent a lot of effort bringing in great speakers, sometimes from around the world, and sometimes, of course, we have great faculty on our own campus, and so we have a number of them from campus. And today is one of the new stars of our campus, I would say, Victoria Stodden, who is a professor here at NCSA. She's one of the core faculty members, as well as the Gislis Graduate School of Library and Information Science, where she's an associate professor. She's also, to give you a hint of her breadth of activity, she is a professor, a faculty affiliate in the College of Law, the Department of Statistics, and the Department of Computer Science. And that seems like an unusual combination. And I'll just give a little bit of background. I met Victoria in, I guess it was 2009. There was a meeting in Italy that actually Susie Iacono from NSF, I was at NSF at the time, suggested you really ought to go to this meeting. And I was like, okay. So I went to this thing, and it was on interdisciplinary research and the kind of challenges of modern times, with particularly where digital methods are becoming more and more prevalent. And in fact, virtually there's no field of research, whether it's in the humanities or in science of physics and astronomy or anywhere in between, engineering and so on, that is not deeply touched by this. And it raises many, many new questions. And it's also seemed very much of a paradox to me that in an era where you have the ability in principle to exactly reproduce what you're doing, because you have digital methods, and of course you can exactly reproduce digital things, right? You can copy things at the bit level. It's becoming increasingly difficult to actually reproduce what you've done in a digital world because of all of the challenges that we have, versioning, the fact that we use different kinds of systems, things change so fast, software changes so fast, and so on. And so Victoria was one of the very early people who began to really promote this as a fundamental issue. And I've been inspired by some of my first discussions with Victoria back in Italy, way back in 2009, so that virtually every talk I give, I start off with a picture of Galileo as one of the early sort of fathers of science, having to set up the scientific method around reproducibility of science. And yet now we have a bigger problem than ever with this. So just, and at that time, I think, Victoria, you were a postdoc of some sort at Harvard, and so in the law school of all things. And so Victoria, with a background in law and statistics from Stanford, with degrees in both subjects, has been very broad. And so then she went on from Harvard to Yale, where she was also associated with the Yale Law School, and then moved very naturally for somebody like Victoria to the Columbia Department of Statistics, and then very naturally to a place like NCSA in the Graduate School of Library and Information Science. So it gives you an idea of the breadth of Victoria's interests, and the fact that this problem is very, very broad and very deep, and we're pleased to have one of the leaders here. So I'll just say a couple more things about Victoria. She co-chairs the NSF Advisory Committee on Computation on Cyber Infrastructure, which is a very important activity there, and also is on the advisory committee for the Computer and Information Science Advisory Committee at NSF as well. She's also serving on the National Academy's Committee on Responsible Science, and she's written a couple of books which have come out in the last year, one on privacy, big data, and the public good, and one on implementing reproducible research. So, I have one other business announcement to say before I let Victoria come up here. We have a reception afterwards. If you've been to these previously and you find that I always forget to announce this, so afterwards there will be a reception out front there with some nice goodies for eating, and I hope you'll take some time to get to know each other and also talk to Victoria there. And next semester, of course, we're starting this up again, and we're in the process of finalizing the speakers. If you have any last-minute suggestions, please let us know. We might be able to fit in a couple of more, but it's a very good series for us. So, thank you, Victoria. It's up to you now.
Okay. Well, it's really a pleasure to be here, and I didn't anticipate such a wonderful introduction. I'd forgotten a lot of that stuff, so I'll try not to disappoint you with the talk today. So my title, toward reliable and reproducible inference in big data. You can see from the title that I think there's a little bit of a problem that we're having here, and I'm using big data sort of as a euphemism for I think what Ed was calling this digitization of science that really spreads across many different fields in the scientific landscape. So what I'd like to do today is actually go through and try and motivate issues around this problem and provide some frames for how we might think about addressing this and understanding what the issues are. And then there have been some solutions and people are chipping away at this, which you would expect. And so I'll talk about maybe some of those solutions, including one that I've been working on. And then I will end the talk with a discussion around an issue that is new for many scientists. When you put stuff on the web, you run headlong into IP law. So as Ed mentioned, some of my experiences in law, so I've been trying to untangle some of these intellectual property issues around code sharing, data sharing, and so on. So I'll talk about this. And I'm very much looking forward to a discussion and questions at the end. Okay, so when I started thinking about this, actually it was during my thesis, as I'd mentioned, at Stanford, and I was interested in whether or not this issue around digitization was important and whether or not there were any ramifications of this digitization. So my idea at the time was look at one of the flagship journals in the field of statistics, which is the Journal of the American Statistical Association. So I went back to 1996. My thesis was submitted in 2006, so I went back 10 years. And at the time in JASA, about half the articles were computational in 1996, and then they went to almost all computational in 2006. And then you can see by 2009, everything being published in JASA has some computational component. Either it's a wholly computational article, or they've done an implementation of a proof, or some simulation. There's something that used a computer in there. And then I was interested in, well, could I actually get the code that was associated with these the computational aspects of these articles? So I had a really low bar. Like if they even sort of mentioned that I could pick up software at some place or something, then they could get in this bin of code publicly available. But in 1996, nobody thought about this in the computational articles that I looked at. Up to 2006, 9%. And then 2011, we're up to 21. I probably need to update that for 2014. But still, so all these articles are computational, and that's not going to change anytime soon. And at least in 2011, I'm looking at 1 in 5, where I actually have a realistic shot of being able to inspect the code and the implementation of the ideas that are being published in these articles. There's a couple of other little data points that I can give you just to start motivating. So John Ioannidis in 2011, he looked at 500 papers, and this is in the biomedical life sciences community, and he tried to see how many had the raw data available. He came up with the figure of 9% with the raw data. So think about that associated with inability to access the software, and already we have this problem of understanding how a researcher went from raw data through to what's published in the actual paper itself. Okay, so I won't have time to discuss this in detail, so I'll just open with a teaser. In a forthcoming article, I have an estimate that about 27% of the papers that are published today in Science magazine are actually reproducible in a computational sense. Okay, maybe I'll get back to that at the end. Okay, so let me step back and start motivating this for you. So as Ed mentioned, thinking about the scientific method, traditionally, we have 2 branches, the way we think about science, and the oldest is the deductive branch, so mathematics and logic going back to the Greeks or beyond, and this quickly fell short when we were trying to understand how our world worked. We couldn't do things like inference or induction, so we developed the second branch of the scientific method, comprising a different set of methods, a different set of approaches and standards. And this is really our statistical analysis of controlled experiments. So now there's a lot of hype. I'm sure everybody in this room has heard a discussion of these new branches of the scientific method. So branch 3, branch 4, driven by computational aspects of scientific research, large-scale simulations, data-driven computational science. So you can see I'm dubious. Many claim this. So let me expand on that a little bit more. So I poked around on the web, and not to sort of pick on any one in particular, but you can see this, this website I found on the left. So this is a workshop at NIST from, as you can probably even tell without reading it, from 1995, Modeling and Simulation Multi-Laboratory Strategic Planning Workshop. The reason I put this up here, and I pulled the text out because you can't really read that from where you are, there's a little quote in here: "It is common now to consider computation as a third branch of science besides theory and experiment." So it's common in 1995 to just accept this. So I also point you to this book that probably many of you have seen. It came out in 2009. It was a co-edited volume from Microsoft with many wonderful authors in there. But if you look right in the preface of the book, it says the book is about a new fourth paradigm for science based on data-intensive computing. So there are these assertions out there. They've been out there for more than more than a decade. Okay, so let's break this down a little further. So the impact of technology. So I believe we can parcel out how technology is impacting science into three groups. I'm leaving aside, so the scientific research process, and I'm leaving aside the World Wide Web and dissemination, which is another impact. So the first one, big data, data-driven discovery, high-dimensional data. We've got many more variables and observations. This is a whole new paradigm for how we might actually think about data, what methods we would use. All these issues that travel with scale are adherent in big data. The second one we've seen, aside from our national obsession with collecting data, is a huge increase in computational power. So this feels a little silly to sit here and say that in NCSA, but this is one of the driving factors that's really fundamentally changed how we carry out science. Simulations of the complete evolution of a physical system, run it again, change the parameters. We can ask new questions that we couldn't have asked before this and have new answers and new science emerging. Okay, so those two I think probably most of you have thought about. The third one I hear almost no discussion of, and I think it's just as important as the first two. Real, bona fide scientific contributions, deep intellectual contributions to science are now appearing only in software. This is software, generally speaking. Hopefully at the beginning of the talk I was motivating you there's a problem with access to code. These are methods, innovations that are not available largely to the scientific community, not for nefarious reasons, but for reasons I'll get into. And the fact that these contributions appearing in software, whether it's clever implementations, whether it's statistical methods, this thinking is not emerging out into the larger scientific community. So I put a screenshot of a YouTube video where Leora Patchter, who is a professor at UC Berkeley, giving this impassioned talk, and I pulled out a little quote, and he's saying the software contains ideas that enable biology. So this isn't something that is written in the PDF and sort of implicitly available in the software. This is really uniquely available in the code. Okay, so stepping back one step further and thinking about how this interacts with the scientific method as I outlined it. So why do we have the scientific method? Our fundamental driving reason is because error is ubiquitous. We want to communicate the results that we think are as correct as possible. I have an obligation, if I'm disseminating these results, to try and convince you I've done everything I can to root error out of the research process, and this is as close to truth as I can possibly get. So in the deductive branch, the way that they've implemented this is, we all know, they have a well-defined concept of a proof. You wouldn't think of publishing a mathematical finding and just saying, trust me around it. Of course, that it'd be the most ridiculous thing on the planet. I mean, you wouldn't even get taken seriously. But you need to give the proof that steps through how you actually arrived at that conclusion. That's possibly even more important than the conclusion itself. In the empirical branch, we have an entire machinery around hypothesis testing, use of appropriate statistical methods, and then very structured ways that we communicate this, and like a method section and how our protocols are actually communicated. Again, in journals, if you have a method section laid out, which is extremely common, you won't be able to publish unless you complete the method section. And the idea core is around this idea of transparency and rooting out error out of the research that's been done. So my claim, computation presents only a potential third or fourth branch of the scientific method until we develop those comparable standards. And I'm okay making what sounds like something of a harsh statement. We've had maybe 2 decades to be thinking about this. These other branches of the scientific method have had hundreds of years to come up with their standards. But I think framing this as, well, what's our version of a proof as computational scientists is an important step towards thinking about how we start to frame solutions. Okay, so many of you have probably seen some of these articles. So these, I think they're all less than 18 months old, maybe less than 12 months. And I just pulled pieces from a popular press and also from some of our top scientific journals to highlight these issues around this credibility crisis. So when we don't have these standards around elevating computational science to a third or fourth or whatever you want to call it branch of the scientific method, we run this risk of a credibility crisis in the work that we're actually doing. So I'm sure many of you saw last October, 2013, so I guess a little more than 12 months, Economist did a special issue on how science goes wrong. Their focus there was in a lot of life sciences, bioinformatics, but there's plenty in there for us to think about as computational scientists. In Nature, announcement reducing your reproducibility, that we must try harder as scientists. NIH tackles irreproducibility in science. Over on the left, you can see an op-ed by the editor-in-chief, Marcia McNutt, just called reproducibility. And then the LA Times is informing us that science has lost its way at a big cost to humanity and so on. So this is good in the sense that we're taking on and we're tackling and we're addressing these issues. However, the subtext here is there's also a responsibility around public trust in science, and maintaining this trust is something that's very important and hard to get back if we lose it. Okay, so issues around reproducibility, I found it very useful in discussions to parse out this term. As soon as I say reproducibility, probably all of you have a different idea of what this actually means. And so I think, and especially it's very field dependent how people understand the word reproducibility. So I found it useful to label a branch of problems in reproducibility as empirical reproducibility issues. If you think about those images on the previous slide, how Nature was saying we must try harder, there are many problems that are being discussed under the rubric of reproducibility today that are really failures of branch 2, traditional science, tracking the actual methods and steps that were carried out, say at a physical wet lab, for example, or can I get reagents. I put this under empirical reproducibility because, in my opinion, this is really, in a sense, a solved problem. It's now an implementation issue. And so there isn't really anything new to think about. It's more like, are we adhering properly to the scientific method as established? I contrast that with computational reproducibility, so that's where I opened the talk. So how has technology impacted how we carry out science? Are there issues that we need to think about from this impact in terms of dissemination, in terms of the scientific method? Hopefully I'm starting to convince you that I think that the answer to that is yes. So issues around digitization, code, data, all of this new stuff that's been happening in scientific research over the last couple of decades, that falls in computational reproducibility. So I've kind of tried to give some examples here. So empirical reproducibility, what science and nature are sort of trying to wrap their minds around. In computational reproducibility, this is just an article I grabbed that I'm a co-author on, so it wasn't a random article. Setting the default to reproducible in computational science research. So that was from 2013, talking about access to code, access to data, standards for delivery of code, standards for delivery of data. The final category that I found it useful for thinking about different aspects of reproducibility is statistical reproducibility. So what falls in that bin would be things like, have you used the appropriate statistical methods? Are your statistical inferences valid, reproducible? Will they turn up in an independent implementation the way they did in your research? I will talk a little bit more about particularly the last two, less about empirical reproducibility. In my opinion, as I mentioned, this is more about implementing standards we have. The last two are almost, in a sense, wide open areas on how we actually have these interfacing with the scientific method. Okay, so when I was a PhD student at Stanford, my advisor was David Donahoe, and David Donahoe was inspired by another professor at Stanford in geophysics, John Claerbout. In 1991 or 1992, John Claerbout stopped signing students' theses unless he could effectively hit return and regenerate their thesis, figures and all. And he had, his system was in-house, within his lab. It was maintained to be able to allow this to happen without much burden for the students. And that was just the mode of how that lab operated. And he called that really reproducible research. And this is paraphrased by my advisor a few years ago. And he says, the idea is an article about computational science in a scientific publication is not the scholarship itself. It's merely advertising of the scholarship. The actual scholarship is the complete set of instructions and data which generated the figures, tables, and results. So I think this has been a useful frame, at least for me, in thinking about this, and it knits together these ideas, for example, how I believe we're seeing these scientific contributions appearing only in the software, for example, that aren't actually captured in that PDF that we all value so highly in science. Okay, so I'm just going to take a few moments and talk about the statistical aspects of reproducibility, particularly as it interfaces with big data, and I see more and more fields that have been traditionally descriptive or have computational experimentation taking on issues around inference and statistics and becoming more empirical in the way that they carry out their research. So I'll mention a few of these statistical issues that can undermine reproducibility that happen all the time in all sorts of research across all sorts of fields. These are wide open problems, they're not theoretical that I'm thinking might happen. Some of these are really even just how the research is carried out in fields as a standard. So false discovery, you discover things in the data, maybe using inappropriate statistical tests that aren't actually real. So of course in a new data set or using more appropriate statistical methods, you don't get the same results. Doing something like lots and lots of tests, so chasing significance, p-hacking, file drawer problem, doing lots of statistical tests until you get that one that matches the theory that you want to publish, and then sort of chucking all the other ones in that file drawer. So that's, in some fields it's changing, but in some fields that's a normal way of carrying out business, and of course you can't imagine that those would ever replicate if you're choosing, sort of cherry picking the results that you think are the ones that you would like to communicate. So that also is overuse, misuse of p-values, heavy reliance on p-values in many, many fields as a threshold for publication, unfortunately, which pushes all that p-hacking and so on. So sensitivity analysis, multiple testing, poor reporting, tracking practices, many of the processes that a scientist goes through in finding results, so in computational work as well as in empirical work, just get lost, right? They're never really documented and make it into the paper. They don't have to be forgotten and sort of part of tacit knowledge. They could be included, and we could do a better job of actually reporting. One of the things that's almost never discussed is how you've actually cleaned your data, merged your data set. What have you done with outliers? All that pre-processing that a data set goes through before the application of statistical methods can really change your results. A slight difference in how you treat outliers can dramatically shift and change results. Okay, a couple of other things I'll just quickly mention. Poor statistical methods, non-random sampling, very common, inappropriate tests, application of inappropriate models. All models are inappropriate in some sense, but it's about understanding when you can properly apply this to a data set or a problem and when you actually can't. I'll come back to this a little bit at the end of the talk, but how robust is your model to small changes in parameters? Small perturbations in the data. If you have a new draw from a distribution, you apply the same model. The data are slightly different. Do you see substantially the same results, or do you see something sort of wildly different? So the statistical methods themselves can actually be very unstable. And then there's all the human issues. So investigators may be biased to previous findings. In fact, we reward publication of work that builds on previously published work, whether or not that previously published work is correct, conflicts of interest, and so on. So we've got lots of incentives to kind of do things in certain ways. So I put this chart up here just to close the discussion on statistical issues. So these are certain physical parameters that physicists were estimating. And what is being plotted here is the publication of the estimate of these constants over time. And so what's interesting, and the reason I put this plot here, is they do tend to converge eventually on the right value or the right constant. However, the way they converge is not a random process and then they kind of all sort of get there. They clearly are related to the previous work. So as we update and get closer and closer to the truth, at least what this plot is showing, we only increment or sort of step away from previously published results, even when they were wildly off to begin with. We don't sort of make leaps towards something that's correct. We kind of need to step in that direction. So this suggests things like bias or publication bias or bias in the types of work that the researchers are actually doing. So these are some particle properties. Okay, so one thing I was interested in is how journals are responding to these statistical issues. And Science in 2004, in January, at the beginning of this year, enacted some new policies around these statistical issues per se. And now publication in Science is going to check for that you have what they call a data handling plan, including things like how you're dealing with outliers, what your thresholds are, or how you're characterizing them. Do you have the appropriate sample size to allow you to make the inferences and detect the real effects that are in the data? Do you have random treatment of your samples, or is there an implicit bias or something that people should be aware of? And was the experimenter blind to the conduct of the experiment, or maybe they were sort of in there manipulating results as they go? And Science also added statisticians to their board of reviewing editors to try and take this problem on. So there's some recognition that these statistical issues are posing a real problem to reproducibility. Okay, so onto the computational aspects, so computational reproducibility. I've done a few pieces of research to try and understand how these issues are being dealt with and whether these are actually successful solutions. So the first one I looked at was, what are journals doing? Do they have a responsibility? If you think about what happens to scientific results as they're being developed in the research pipeline, as they go through to publication, even as they were originally funded, is the researcher going to get promoted or hired? There's lots of different levers and incentives that a researcher is subject to that can impact whether these results are reproducible, or sort of you think about, well, whose problem is it that we publish work that's not reproducible for whatever reason? There's lots of answers to that question. One of them is the journals. So I was interested in how journals were actually addressing these issues, if they were at all. So I took a sample of 170 journals, and I chose 4 ISI classifications: statistics and probability, mathematics, computational biology, or 3, I guess, multidisciplinary science, and so I made sure nature and science were in there. And the reason for choosing these is I was hoping there was a strong computational aspect to what they were publishing. It's not really fair to ask about code and data release strategies if it's a philosophy journal or something. Okay, so we pulled a lot of information around these journals, impact factor citations, and we looked at their publication policies around code and data, what the author guidelines actually said in June of 2011 and June of 2012. So I also wanted to get a sense of that first derivative, how these policies were changing and with what type of pace. So journal data sharing. So I grouped the types of statements journals were making around data sharing into 3 categories. So they require it. They're not going to publish your results unless you actually make the data available. And when it says barring exceptions, there are always exceptions around, say, for example, patient privacy and HIPAA and so on. I would like those to be the exception rather than kind of dominating the discussion. But there are always reasons data can't legitimately be openly shared. So required is a condition of publication. Required, but we may publish a paper anyway, so there's that. There's many journals that said we encourage the availability of data, or they somehow have some language that addresses it, but they stop short of actually making this a requirement to publication. They mention things like maybe we'll host it for you, maybe we'll review it for you, but they don't make it a requirement. Sometimes there's language where it's implied that really what they want you to do is share your data, and then of course there are journals that just don't mention the issue at all. So the numbers are somewhat small, but changing. So you can see required went from 10.6 to 11.2%, and then a big one in required, but we will still make our same editorial decisions either way. 1.7 up to about 6% of the journals. And then encouraging went from about 21 to about 17.5%, so a little bit of shuffling. These ones mostly shifted up into stronger requirements. The language that implied it went from nothing to about 3% of the journals. So overall, the upshot is that in 2012, about 62% of the journals didn't mention this issue at all. So we're looking at about 38% that had taken this on. So that might seem, given the magnitude and the importance of the problem, it might seem like still a small number to you. However, that was more than I expected in there. So I really thought these journals had taken on, really actively taken on this problem, and are still taking it on. So I did the same thing for code. So what do these journals say about code sharing? So this is much, much lower. And you can kind of even get a sense that this might be the case because all of these sort of scientific policy discussions, you often hear discussions of data sharing, data availability. You rarely hear people mentioning software or code. I think communities like here at NCSA, it's different. And in most of the discussions I hear about this, code is an afterthought or not even considered. And in my view, they're completely coupled. Like, I'm not sure how you could have data available, particularly when you think about reproducibility, and not have code available as well. I mean, you've got to sort of store and access the data and so on. So I think these are really coupled, and I think the discussion will get there. However, right now, it's very bifurcated, and I think people really don't address code the way that they should be. I'm speaking in very, very broad terms. Okay, so for code, you can see things are pretty static. 2011, 2012, requirements around code disclosure are 3.5%, so I also need to disclose to you that those journals are sort of software journals. So ones where it wouldn't even make sense to publish without making your code available. So it's really a baseline. So I was encouraged by seeing this number go from 10% up to 12.4, so some recognition that software is important, you should be getting this out there with your article. Implied going up to 2% from 0. So I've got 79% of the journals in this sample not taking on the issue at all, but it wasn't 100%. Okay, so quick findings on this study. The high impact factor journals, those were the ones that were comfortable making these changes. The lower impact factor journals were hesitant, it seemed, to ask more of their authors. So really we were seeing this sort of top-down, sort of the policy changes happening at high impact journals and kind of sort of dripping down to the lower impact journals. I think the adoption is relatively rapid. Those are significant changes from 2011 to 12. And then the last thing that I'm going to mention is data supplemental materials policies appear to lead software policy. So I also looked at, I won't mention it here, but I looked at supplemental materials, whether there's a relationship with open access to the literature and so on. Okay, so then the other thing I was thinking about, well, what about the human being involved? So the researcher is carrying this out. The researcher might be a postdoc, a grad student. It could be someone very early in their research career. It could be a very senior person. And they're subject to different incentives and reasons why they may or may not share code. So I actually surveyed the NIPS community, so Neural Information Processing Systems. You might be familiar with that conference. It's one of the, if not the top machine learning conference. And so I surveyed, I think we had 1758 NIPS registrants, and I cut this sample down to people who were in the US and in academic institutions. These were the folks I was interested in for this particular survey. And so after all the piloting, and so eventually, excuse me, I sent the survey out to 638 and got a 23% response rate just based on a cold email, which I thought was pretty phenomenal and kind of said something about the importance of this issue among people who were presenting at NIPS. So my questions were, for your NIPS paper, did you share the code? Why or why not? Did you share the data? Why or why not? And there was more to the survey than that, but that's the upshot of it. So reasons people actually shared, if they did share, you can see things like these kind of lofty ideals coming out, encouraging scientific advancement, encouraging sharing in others, being a good community member. Sharing is obviously an important norm in the community they want to respect. setting a standard for the field. So these are all sort of very much that are not kind of, I don't mean selfish in a pejorative sense, but they weren't sort of inward-looking reasons for doing the sharing. Improving the caliber of research, and then sort of in these sort of lower percentage reasons, you start to see a little bit more of sort of personal incentives creeping in. I want to get others working on this problem. I think it's a really important problem. I can increase publicity for my work. I can get feedback if I share code data more easily this way, and maybe I'll even pick up a few collaborators as I go. And it turns out all of those are absolutely true when you do it. Okay, so I also asked if you didn't share, what was the problem? So what stopped you from doing this? And I actually had one comment that said this first one, time to document and clean up, was basically important on a log scale. It just dominated all other reasons, which to me really speaks to this incentives issue in the way that we share research and the way that we value research. I've never met a scientist who enjoys writing a paper, but they all get it done, right? So I think that we're not really rewarding this sharing and preparing of code and data, which are not, it's non-trivial to get this ready for reuse by even other people in your same community who have the same amount of scientific knowledge and basis for analysis as you do. I don't want to deal with questions from users. I'm going to get my work stolen. I won't get attribution. These two surprised me, the next two, possibility of patents and legal barriers. So these intellectual property issues actually were pretty high up in the way scientists decided to not share, or their fear of sort of sharing or releasing something. It's just too onerous. I have to go through all these hoops with administrators. I may be scooped. I might lose future publications. Competitors can get an advantage, and it's just too big. I don't even know where to put it. Where should I put this stuff? Okay, so problems all over the place. So what are some of the solutions? I'll go a little bit more quickly in some of the solutions. And by the way, I should have mentioned my slides are on my website. So if you'd prefer to just look at them locally, feel free. And most of the stuff's hot linked in here, so you can just sort of navigate away from the slides if something interests you. So there was a workshop in December of 2012 that I co-organized on with 6 people here, and called Reproducibility in Computational Experimental Mathematics. And this is a week-long ICERM workshop at Brown University, and we got all these people together from many different areas of research, also stakeholders from funding agencies like DOE, NSF, and so on, and journal folks, editors, and society folks like ACM, and so on. And we basically spent the week in breakout groups and brainstorming and came up with a workshop report. And so this report here, setting the default to reproducible, we have a couple of sort of published descriptions pointing to the report, saying that our default really should be availability of code, availability of data that went into the publication of your results. Then if there's issues on why you can't share that, that becomes the exception, rather than the situation which is currently the case, although it's changing, where you see a few exceptional researchers kind of putting this stuff out there, and they're really not the norm. Okay, so I put this up not to blind you with a blizzard of words, but I thought this audience might find it useful, so I'm just going to step you through this. This is one of the tables from the ICERM workshop report, where what we tried to do was hash out what should be included when you actually share code. What's the information that's valuable? So if we could come up with, even if it doesn't suit all situations, something of a checklist of what's important to include, this might help move the ball forward. So do you have assertions, a precise statement of assertions made in the paper? Do you have a statement of your computational approach, rigorous test of hypothesized assertions? Are you citing all your software? Complete statements of references to every algorithm, salient details of auxiliary software used in the computation. Did you talk about the hardware? So there aren't very many papers I've seen in my experience that really talk about the details of the hardware implementation, where their code was actually run. What's your test environment, hardware, software, number of processors utilized, for example? What's the details of your data reduction, any statistical methods that you implemented? Are there parameters? How did you choose your parameters? Was this adequate? Was your grid resolution level chosen correctly? How does that interact with how you might actually interpret the results? Did you give me all the run parameters in your paper? Can I actually do this? Is there a full statement of the results? Availability of code, input data, output data, some reasonable level of documentation. Which precise functions were called? What were the settings on these functions? Are there instructions for repeating the computational experiments described in the paper? Did you tell me alternative avenues of exploration that you took that actually didn't lead anywhere, but but were still important discoveries in their own right. So sort of negative findings. And then is everything cited? Code and data. So this was our first crack at the end of 2012 of trying to establish some standards or thinking about how we might actually coherently publish computational research. Okay, I also wanted to mention, it might be of interest to this audience, there's a workshop I participated in that was prepended onto Exceed 14 around reproducibility. And the focus was really reproducibility at scale. So what do you do when you have extremely large computational systems? You're not just going to virtualize these HPC systems. So what can we do to actually step towards a notion of reproducibility in these settings? And we are working hard, and we have a workshop report coming from this that updates many of those ICERM criteria and discusses the scale issues in particular, and especially the role of intermediary software such as Exceed in tracking many of the issues and details that you would actually need to reproduce these results, and even just to understand the results. So stay tuned for this one. Many tools have actually been popping up to try and resolve these issues in computational science around reproducibility, particularly around data access, code access. These are hot linked. There are many more, so I don't pretend to be comprehensive here, but I wanted to just mention that there's lots that are coming up all the time. They're amazingly cool. Most of this is just being done by faculty in their spare time because I think it's a really important problem. These aren't sort of big infrastructural or big software companies that have scooped in to try and do this. This is stuff people are hacking at and trying to make available to the community. So I grouped them into approximately 3 groups. They're a little overlapping. So it seems to be a type of tool that is a dissemination platform. So what do you do if you want to share your code and data? How do you make that available? How do you make it persevere over time? For example, how do you track provenance of data and changes in code and versioning and so on? So these dissemination platforms are here. One that I'll mention coming up is Research Compendia, is the one that I've been working on. And then another group, workflow tracking in research environments. So this is really pre-publication, whereas dissemination platform seems to be post-publication affecting the dissemination of research. So pre-publication, how do you capture as you're going all the interesting information that other people would need to understand your results? So there's lots of work happening there. And then there's another sort of hybrid class, embedded publishing. How can I make that PDF more alive, or embed code and data within this, or actually even rerun and check results within the PDF itself or the sort of published document? So I encourage you to take a look. Some of them are just really amazing. Okay, so I've been spending some time working on Research Compendia. So the idea of Research Compendia is it's promoting this notion of, instead of publishing the one paper, we publish a compendia of paper, data, and code that are all linked as a triple. And so the idea here with Research Compendia, you can see we just sort of pilot in many senses to try and understand how scientists are sharing, what their needs are, what the barriers are, and better understand this. So we're trying to link data and code to these published claims, so that this is persistent. This is something, if you see a publication, you can grab the data and code. We're trying to enable the reuse of both of these objects. Provide guides for sharing for researchers. Many researchers don't really know what's acceptable or what's appropriate for sharing data and sharing code. As I'll mention, we can actually certify published results because we'll run the data and the code, and if we can get the results in your paper, we can sort of say, you know, as a third party, we were able to get these docs. And actually, I'll show you in a moment how you could do that too. As we collect data and code, I can envision something like much larger data sets or amalgamations of the data sets submitted where we can run software and solutions across much larger data sets and actually validate findings that way, and do things like stability and sensitivity checks. Okay, so here's the way it works. So there's one compendium page associated with every publication. So this top blue here will link out to the publication. If it's open access publication, we'll grab a copy, which this one actually is. So you can actually, it's a little tough. You can click on this article button here and grab the article, but if it's behind a paywall, we'll just link out. And then there's buttons you can see down there. Maybe it's a little bit hard to see, but for grabbing the code and grabbing the data. And so what's interesting here is we didn't just copy the abstract from the paper and put the authors from the paper here, although that's fine and authors can do that. You could actually reward people who are doing software programming support, for example, or development in the project that maybe weren't rewarded in the traditional way that they should have been, or data curators, for example, could all be here. And the abstract refers to the code and data. You've got an abstract on your paper. So now we get to talk about code and data. And you can see licensing information and so on here. So I wanted to also mention our more experimental area in Research Compendia, where we actually added another button here. A little bit hard for you to see, but this verify button here. So we'll implement the code, and we'll run the code on the data supplied by the author. And so in this case, these random survival forests for high-dimensional data. And you can actually run that and get the results and check for yourself that it matched the published results. Of course, we're running it, so in a sense, you're trusting us, but you don't like that, you can grab code data and so on and do it on your own system if you want, which, as we all know, it's non-trivial. And you can see we're also assigning document object identifiers to code and to data here, so they have some permanence and persistence. They are embedded hierarchically with the DOI for the paper and the DOI for the compendia page itself. And then you can see information. They can grab the code that we're using to do the verification and see the runs and so on that other people have done. So it's all open source. So here's our page on GitHub. And that's a philosophical choice that we made in development, in that if we're interested in transparency, reproducibility, it kind of makes sense that we want to make sure that our own work is transparent and reproducible, aside from the issue that we want people to be able to extend this, use it as a platform, stand up their own versions of Research Compendia if that's what's useful for them. I mean, that's something that can also move this reproducibility ball forward. We license it under the MIT license. So I'm a little bit, well, maybe I'll take the next 7 minutes on an IP discussion, as I mentioned at the beginning. But we license this using the MIT license because that's a deliberate choice to make this as, one, as openly available as possible, and two, as close to traditional scientific norms as we could. So the MIT license is pretty much, to summarize, pretty much an attribution license. If you want to use this, we're looking for attribution and changes and so on. And that aligns, in my opinion, the most closely to how we carry out scientific research. Typically what we'll do is say, here are our scientific findings. This goes out to the community. Do what you will with them. Hopefully build on them, reuse them, and extend them. Hopefully they're useful, but we do want attribution citation. Okay, so that leads into the discussion, the last part of my talk, which is around these legal barriers to code sharing and data sharing. So the first one, and the primary one I'm going to talk about, is copyright. The reason this one is, I think, deserving of our attention is that copyright applies to your original expressions of ideas by default. So this isn't something that you go and you register and you seek, and this is something that is exceptional and attached to your work. It's on your figures, it's on your code, there was a nice descriptive phrase that I heard once, that copyright follows your pen across the page. So it's something that every single computational scientist has to address and deal with. So if you look into the Constitution, so copyright goes all the way back to the Constitution. It says to promote the progress of science, so that's right in there. Who knew in the Constitution? To promote the progress of science and useful arts by securing for limited times to authors and inventors the exclusive right to their respective writings and discoveries. So as I mentioned, original expression of ideas falls under copyright by default. Your papers, codes, figures, tables, all of this stuff, this original expression of your ideas, as soon as it's in fixed form. And what copyright does is it secures exclusive rights vested in the author, so you're the only one who can reproduce the work, and you're the only one who can prepare derivative works based on the original. So that's a little shocking, right? Both of those exactly orthogonal to what we're trying to do as scientists. I want other people to reproduce my work. This is part of our verification, validation of results, transparency, rooting out error. We have a whole machinery of norms behind this. And also, I would really love it if you prepared derivative works based on my work. For example, you write a paper building on my results and citing me. This is like the greatest thing that can happen to a scientist, right? Well, presumably it's a positive cite. But having this work be useful and impactful in the community, copyright blocks both of these core scientific ideals. Now, I won't go into it in detail, but copyright has some exceptions, like, for example, fair use. But these exceptions and limitations do not extend to the whole of scientific research. This is a real barrier that all of us have to deal with. So when I started thinking about this, in the context of being a PhD student in David Donahoe's group, where we were trying to produce reproducible research. We would share code, we would share data, and so we had all these IP issues kind of flying in our face. I didn't know much about it at that point. I did my law degree after my PhD, but I went back and I started kind of ruminating on, well, maybe other people have run into something similar. So, of course, Richard Stallman has thought about this issue a lot and is the pioneer in one solution to this issue. So he is known probably as the founder of the open source software movement, and one of the credits that is given to the success of the open source software movement is his development of a license that got around these copyright barriers and allowed the sharing of software that was open source. So what he did is he pioneered the idea of having a license. Instead of saying, okay, something's under copyright and I need to ask you if I can reproduce and ask you if I can prepare a derivative work, I'll just pre-permission your use of this work. So that was Stallman. And he said, well, I'll just have some text that travels with my software. You don't have to ask me permission. I'm just in advance giving you permission on how you can do this. And so it's communicating these alternative terms of use to other developers rather than allowing the default of copyright to persist. So this was wildly successful. He came up with, the first one was the GNU public license that allowed this open source software movement to develop. There are hundreds and hundreds of software licenses now. There's a few I listed here. It's just been this incredibly successful idea. Like I have a link here where you can just, if you're really bored, peruse the zillions of them. Okay, so this idea was extended by Larry Lessig. So he was a professor at Stanford Law School when I was there, and he developed Creative Commons, which probably people have heard of in this room. He did it with Hal Abelson and also Eric Eldred. The three of them got together, and in 2001 they founded Creative Commons. The idea was Stallman's incredibly prolific idea worked for code, for software. But what about artists who want to share, say, pictures, movies, collages, whatever it is, sound, music, and so on the web? GPL kind of it had a lot of stuff in there around software and around code and open source. It didn't really make sense in the context of, say, sharing like a mixtape or something on the web. So Creative Commons was designed to plug that gap. So for artistic works, he developed a series of licenses that would allow people to do the same thing, prepend, reuse permissions with their work that traveled with their work. So he's adapting this open source software approach to artistic and creative digital works. So my question was, well, so we've got this history of people thinking about this problem. Can we extend this now to scientific works? They're different from artistic works. They're different from open source software in a way. We've got a lot more stuff going on. We've got this huge legacy of norms. We've got data involved. We've got PDFs involved. We've got lots of stakeholders involved. So I developed this idea of the reproducible research standard, and instead of writing new licenses, what I did was break apart the work that we produce as scientists and see which components could be applied, which licenses could be applied to the components in a way that's respectful of scientific norms or aligns with scientific norms. So what I suggested was our media components like text, figures, release under Creative Commons Attribution License. Again, this idea that we put our work out there, we're asking for attribution, nothing else. Now I'm conveniently ignoring the fact that many scientists will sign copyright over to a publisher in this, but let's leave that issue aside for now. If you have rights over all this, which you do at some point, ideally we would release this under a Creative Commons Attribution License. Code components go out under modified BSD or MIT license. You saw that earlier. These very lightweight, basically attribution-only licenses. And then data, I suggest just put data into the public domain, or maybe there's an attribution license that you can attach for data. And I'll come back to the point around data. It's a little bit subtle and I think fairly interesting, so I'll come back to it in one moment. But the idea of this sort of triple of licensing was to remove copyright's barrier to reproducible research and realign our IP framework with the long-standing scientific norms. Okay, so for data, I think data is really fascinating. So there's no copyright on raw facts in the US. There is, for example, copyright in many other countries, for example, in Europe, on raw facts. So it opens up these very interesting issues about how we actually share and permission data for reuse, particularly since most of our collaborations are international in science. So there was a case called Feist that went to the Supreme Court in 1991, and this is where facts were determined not to have copyright status in the US. It went back to actually to phone books, like so much of this stuff somehow comes back to phone companies. Original selection and arrangement of facts is copyrightable, not the raw facts themselves, is the upshot of the finding. So what this means in science, think about the last data set you either produced or you used. What's a raw fact in that context? This wasn't written for science, right? And so it's not even clear to me what qualifies as a raw fact versus a selection and arrangement of a raw fact in the scientific context. There isn't case law that's fleshed this out, and actually I hope we never get to that and that we can just sort this out ourselves. But what it means is there's a possibility of this residual copyright in data. So if you've done very clever selection and arrangement, say different data sets and pulled them together, I think you could probably argue that your data set has some residual copyright associated with it. So putting this into the public domain just makes that not a problem. And if you do have code on how you've merged the data sets, of course that can have an attribution license attached. Okay, the last thing that I'll mention is the ByDoll Act. So this was passed in 1980, and again, you'll notice with the date that that's something that was passed in Congress before anyone was thinking about, in Congress, we're thinking about computational interactions with science. Scientists were thinking about it then, but not when ByDoll was passed, not by the authors. And so what ByDoll does is it says federal agency grantees, so you get money from a federal agency like NSF, you're charged with using the patent system to actually disseminate the work and the inventions that are coming from the federal funding. And the idea behind ByDoll, believe it or not, was increased transparency. This idea that the use of the patent system and licensing could incentivize the transfer of these inventions out into the larger community for commercialization and for other benefits. Now I see this potential with software patents. Again, this wasn't something that those Congress people were thinking about in 1980, but with software patents, I think there's a potential for conflict between sort of open reproducible research, the way that I've been talking about today, and incentives to patent that happen at the institutional research level and that have come straight out of ByDoll. They're perfectly legitimate in a legal sense here. So that's something I just throw out there to think about. So this is Stanford's agreement. We all signed this agreement of putting our inventions over to the university when we got hired. Okay, so final slide that I'll finish on. So a couple of papers around encouraging people to share the code, top 10 reasons not to share your code and why you should anyway, and how this movement in the scientific community is starting to fly in the face a little bit with ByDoll and these structures that have been in place for a long time. So we're really questioning a lot of the way that we do science because of these technological changes. Okay, so I'll stop there, and I know I used a lot of time, but I would love to take questions if we can. Thank you. Thank you very much.
So, do we have a couple of questions for Victoria?
Thanks, very good talk. I was wondering if there is some role for education in this. So I'm speaking from my experience. I was never taught proper, research scientific methods. So coming from a computer science background, and I never, even during my PhD, my supervisors never actually explicitly told me, oh yeah, you should really share your code. You should make it readable. You should make it, not a black box. So it's really a discussion that we should be having very early on in our careers, I feel.
I couldn't agree more. So that's a fantastic point that I don't emphasize enough here. And my own personal experience in having these discussions is the more senior folks probably aren't going to change. It's the junior folks that really are the ones who are able to adopt these methods and carry forward with it. But I think it's even more serious than what you actually touched on. I've given talks, and oftentimes when you give a talk, they'll just sort of fill your day with meetings and so on, and often grad students will be in those meetings. And I have had grad students come up to me and actually be incredibly frustrated by this, that there isn't mentorship on how to do effective computational research. Like, what should they be using GitHub and putting things out there? Does that conflict with ByDoll? I don't know. And how do I preserve my own sense of integrity when I don't want to publish in a closed source journal, but that's high, impact and that could help my career? All these questions that they're not getting, any sense of mentorship around. And these are sort of real ethical issues. And then you underscore that with they worry about the science that's being published when it's not open. And they worry that the quality isn't there, the transparency isn't there, and they lose faith in the system as it's being presented. So I think it's more than just a practical need to solve the problem, because that's where all the education, you have to teach the puppies, right, not the old dogs and so on. So that's where the solution is. That's also where the philosophical alignment is. I think the students are hungry for this kind of stuff and need it, and we almost have a moral obligation to step in and start discussing these issues and talking about this, because the students they all know what open source software is, and they come in and it's confusing that we don't operate in a more transparent way, and we risk losing them, this whole generation.
Another question there?
Yeah, with code, and I guess to some extent with data, the code that I released today may or may not work in 2 years.
Yep.
Whose responsibility is it is there a responsibility to make the code runnable in the future and to make data available? Who pays for the cost of making data available?
Yeah, so these are terrific questions, and that's where the rubber hits the road on both of those, on code and data. So with code, so maybe it doesn't run in 2 years. So there are some code bases, of course, that are hundreds of thousands of lines long, and it's not reasonable to get in and inspect them. But a lot of scientific codes are not like that. And I think there's still value in being able to look at the implementation and see the parameter settings and what they actually did, even if it doesn't run. However, I'm very optimistic that things will continue to run. So one of the things that we did in Research Compendia is we have, so each paper sits in a very lightweight sort of container, and it runs, so all the replication software will run in this container in this sort of isolated way. And so there's some work that's happening at Berkeley, the Berkeley Compute Environment, and in other universities, where the idea is, well, maybe we can sort of pre-hand out these containers. These are sort of standardized reproducible environments, and then the work happens within those containers. So publishing just becomes an act of sort of slotting your container in there. And so I'm much more optimistic about this. However, I don't think it's the end of the world if things don't run, and if they run for a short time, that's still much better than nothing. And I think in my discussions at NSF, I'm also optimistic about resources being dedicated to house persistent availability of data and codes. It's not at all a solved problem. One of the things I didn't mention here is most of this stuff coming from White House and so on about data access and sort of these movement on policies. Also riding with that is, we're not giving you any extra money to do this, it's this unfunded mandate. So this is something that has to change, and I think we're going to see in the next year, 18 months, some actual muscle getting behind this to solve those problems that you're talking about that are huge barriers. I mean, it's if you want to store this stuff, it's not cheap. Yeah, that's great.
Thank you. So I'd like to suggest that we take further questions for Victoria outside, where we have a few snacks. And so if we could thank Victoria again. Thank you very much.